Good evening, students. Hi everyone. My name is Sumit Kundu, and I am a BTech from IIT Bombay. I have done my civil engineering in degree, and I joined as a software engineer just after that. And after which I started my own business in Bombay, and then for some time I sold it off to Naukri.com after some time, and then I started my career as a teacher from 2011. All right, from 2011 to 2018, so this 7 years journey, it has been really wonderful with so many different batches of physics, batches for JEE and medical having passed out in these years. All right, so students, why are we here today? We are here for a session on wave optics. All right, so we are here for wave optics. Now, this is one of the chapters that's definitely very scoring from the JEE point of view, my dear students. Okay, now we all know that light behaves some. I mean, we have got in terms of ray optics, and sometimes it behaves as a particle, and sometimes we have it as a wave. All right. Now, here in this session, now as such, there are certain principles like the Huygens principle, which talks about the wave fronts and how wave fronts are being created, and the direction of the travel, and how do you measure or draw the two wave fronts and all that. So those things are something that we are not going to do out here in today's session, students. Okay. What we are primarily focusing on today's session is we're going to be doing one section of wave optics. Wave property of light, as you would say. Now, going ahead, let me tell you, there are certain phenomena of light. Let me just take a fresh page out here. So there are certain phenomena of light that we all know. So I'm just going to write them down on the left hand side. All right. So students, let's say we've got reflection. We have got refraction. We have interference. All right. And after that, we have got diffraction. And finally, we are having polarization. Now, students, this reflection could actually be explained through via ray plus wave optics. Refraction again via ray plus wave optics. However, students, interference could only be explained via wave, diffraction via wave, and polarization via wave optics. Okay. Now, students, among all these three, I mean, which is the primary focus area of your wave optics, students, what is going to be the focus of today's session? It is going to be your interference. Okay. All right. Now that too in interference, we are going to specifically look at the Young's double slit experiment and certain modifications in that Young's double slit experiment we are going to look at. Okay. So what is interference first of all? Okay. Now, students, we all know, I'm not going to be doing a lot of derivations out here with respect to your interference and things like that. But I would want you to know, interference is like when we have got one wave and we have got another wave coming from two different sides, then certain things happen. Let's say, for example, let's just give you the understanding here. So, say I have got a wave traveling in this particular direction. All right. And students, I have got another wave, let's say this particular wave, all right, which is traveling in the opposite direction. Clear? So say it's traveling in this particular direction. So say this has got an amplitude A1 and this has got an amplitude A2. So in future, somewhere in between, these two waves are going to meet. All right. And at the point when these two waves are basically going to be meeting, all right, there are two things that can happen. Clear? What are the two things that can actually happen? Say this is my wave 1 and this is my wave 2. So this could be my wave 1 and the wave 2 could be above the wave 1 just like this. So here we say that this wave 1 and wave 2 is basically in phase. And as a result of which, what happens, my dear students? The net resultant is something like this. All right. So this is basically called as your constructive. It's called as your constructive interference. All right. However, there could be another possibility that could actually take place. Let's just have a look at that possibility, wherein I could have this as my first wave. All right. I could have this as my first wave, and the second wave would possibly be like this. All right. As a result of which, the combination of these two is going to give me a wave which is going to be lesser than these two. So here what has happened, the net amplitude, if you see here, in this particular case, this amplitude that you see here will be equals to A1 plus A2. That is sum of the amplitude of these individual waves. Okay, that is in case of your constructive interference. Second, in case of destructive interference, this is going to be equals to A1 minus A2. Clear, students? So what happens is that during constructive interference, all right, the net intensity or the net brightness of the light increases, like it becomes more than whatever was the greater of the two. And in case of destructive interference, what happens is it becomes lesser than less of the two. All right. So this is what we see that happens in case of your constructive and your destructive interference. All right. Now here what happens, my dear students, in case of destructive interference? In case of destructive interference, I have the waves out of phase. All right. So previously it was in phase, and right now out here in case of destructive interference, it is out of phase. Now students, there could be anything like in phase and between out of phase. There are many different phases that could be there between the waves. Now technically, if one source is having an intensity I1, so this is like say my source 1, which has got intensity I1, and I've got another source, say S2, it has got a intensity I2, then if they two were to interfere with each other, and we need to find out resultant at a given point, how do we find it out? We use a formula that is I is equal to I1 plus I2 plus 2 root I1 I2 into cos of phi. All right. And what is phi? Phi here is the phase difference, students, between these two waves, okay, that is coming from S1 and coming from S2. All right, just now we saw this is like totally out of phase. Totally out of phase, phi means 180 degree, okay, and in phase, that means theta is equals to 0 degrees. Clear? So like this way. So we can have a phase difference anywhere between 0 degree and 180 degree. That totally depends on that, and based on it I'll be having different values of intensity at a given point where the two waves would be differentiated by a certain phase difference. Is the point clear to everyone? Yes, guys, I think it's enlightenment happened at your end now. So we can go ahead and let's look at one of the very, very basic problems of Young's double slit experiment. Clear? How does the setup look like? Setup is something like this. Okay. We have got uh, a screen in which I've made like two holes. All right, which I've made two holes. So that is like my S1 and S2, and both these holes are basically illuminated by a light. That is your S0. Okay. Now, why do we do that? Why do we have both these lighted up by this? So that they become coherent sources of light. Okay. And here at a distance D, capital D, we have got a screen. All right. Now, for different points on this particular screen, there will be lights coming from both these sources. All right, the lights coming from both these sources, and they are going to interfere in such a way that they will have a particular phase difference between them. Okay, and due to which you will get different values of intensities of light on the screen. Okay, and typically, what do we get? Typically, students, we have got like a very bright light at the center, which is known as your central maxima. So here at the center, what are we going to get? At the center, we are going to get a very bright light. So that is called as your central maxima. All right. And just above the central maxima, you will have a dark patch out here. There's going to be a dark patch out here, and there's going to be a dark patch below here. So this is my dark fringe, and then there is going to be again bright fringe, dark fringe, bright fringe. So this is how it is going to be looking like. Okay, now students, how do we analyze the problems? We simply require one very, very simple concept. We know there is something called as phase difference between the two sources of light coming from these two slits. Okay. Now, besides this phase difference, I know, say for example, I've got a wave out here. Got a wave out here. And here the wave goes this way. Okay. Now, between this point out here, my dear, between this point out here and this point out here, what is the phase difference? The phase difference is that of 2 pi. And corresponding to this phase difference, what is the difference in the path that these 2 points has to travel, that is corresponding to lambda? Okay. So students, if lambda is the phase difference, path difference, now what exactly is the path difference? See here, from this source S1, the light is traveling along this direction to reach point P. So what is the total length of the path covered by the light from S1? It is actually S1P. And what is the total length of path covered by the light in going from S2 to P? It is nothing but S2P. So students, as these two both simultaneously reach point P, okay, what is going to be the path difference? It is nothing but the difference between their actual length of these particular lengths. Okay, so here the path difference is nothing but equals to S1P minus S2P. Clear? So this is the path difference between them. Is this clear? So there is one interesting thing out here, that once you know the path difference, we can link it with the phase difference. Once you link it with the phase difference, okay, we should be able to find out what is the intensity at the different points on the screen. Now let us look at the beauty of this. So if the path difference is lambda, the phase difference is 2 pi. If it is equal to like 1, it is like 2 pi by lambda. And if it is equals to some value delta x, then phase difference will correspondingly become equals to 2 pi by lambda into delta x. So this is the formula which gives me the phase difference. Let me take it on a fresh page, students. This is what is important to you so far. Intensity is equals to I1 plus I2 plus 2 root I1 I2 cos of phi. This is my phase difference. These are the intensities from the two different sources of light. Okay, and we know delta phi, that is nothing but the phase difference. Here I've written is a delta pi, here it is just phi, is equal to 2 pi by lambda into delta x. This is phase difference, and this is path difference. All right, students. So just these two formulas so far important. Clear? Now, what do we else have besides these two formulas? Let's just have a look. Okay. Now, students, if you look at, let's look at this thing again. All right. What I can conclude, like, what is going to be this S1P minus S2P? There's one short way of remembering that. Okay. Look at it. Now, generally what they do is they find out S2P and S1P, they get these values and then like, R1 minus R2 and all that. I do it by a very, very one-step method. Okay. See, this is definitely like 90-degree out here. All right. This entire thing is like 90-degree. If this is like theta, wait, students, I'll do one thing. I'll redraw that entire thing for you so that you can have your piece to have a look at it. Okay. Now I've got, this is, let's say, the central line out here, and you've got the screen here. All right. So light is coming from this point, and let's say this point, and reaching somewhere here. Okay. It's reaching somewhere here. Then, my dear students, this is like your S1P and this is like your S2P. Path difference delta x is going to be equal to S1P minus S2P. This is what? This is nothing but my path difference. How do I find it out in one shot? Simple thing. I'll teach you. Drop a perpendicular from here. Okay, say drop a perpendicular from here. Say it comes somewhere out here. All right. So this is going to be like 90 degrees. Clear? And the central line is also subtending an angle at this point, and we kind of call it as theta. So students, this is going to be like how much? 90 minus theta. Okay. Now see this, that this line and this line, they are actually very close to each other. I mean, if you see S1, between S1 and S2, we call the distance between S1 and S2 is equal to D, S1, S2. That is the distance between the two slits. Between the two slits. Now, if this is like 90 degree, this is also equivalent to like your 90. All right. As a result of which, if this is 90 minus theta, this is also your theta. And then if you take this triangle S1, S2, and some R, let's say, okay, then what is the path difference between this and this is nothing but equals to this, because this is almost equal to this part. So the path difference is this length S2R. So path difference out here, delta x, is nothing but equals to S2R. All right, students, these are very basics. Now here, this can be given as, from this triangle, S2R as nothing but D sine theta. Okay. Now we take, let's say, this point at y, and this distance here as d, my dear students, then simply, since these angles are like, very, very small, I can say my delta x is d sine theta, which is approximately equals to d tan theta. All right. So my delta x comes out to be d tan theta. Y perpendicular by base. Y divided by t. Clear, students? All right. Now, let us just go ahead and let's take up a problem out here. Very simple one. Very, very logical and very, very simple. Now, here what we have learned, that path difference between these two waves reaching a given point here is dy by d. Now, students, one last point that I would like to tell you, that based on this formula that you just saw here, that is the total intensity is equal to I1 plus I2 plus 2 root I1 I2 cos of phi. In this, when it is constructive interference, all right, when it is constructive interference, students, that means intensity is max. Intensity is max. What does it mean? Cos phi should be equals to plus 1. Cos phi equals to plus 1 implies my phi is equals to even multiples of pi. So that is equals to 2n pi, my dear students. Okay. So that is your phi. Acha. Then path difference, phi is equals to what? 2 pi by lambda into delta x should be equals to 2n pi. 2 pi cancel, which implies delta x is equals to n lambda. Students, if delta x, if the path difference between the two sources is equals to m lambda, I'm going to have a constructive interference. Similarly, when I'm going to have a destructive interference, cos phi is going to be minus 1, cos phi is equals to minus 1, then phi should be equals to 2n plus 1 pi by 2. Sorry, 2n plus 1 pi, okay, which will give me my phi is equals to what? 2n plus 1 pi, all right, and then delta x will become 2n plus 1 pi lambda by 2, okay. So let's just look at for destructive interference quickly. Destructive interference. Now, here, students, I have just tried to cover up the very, very basics in my first master class. All right, just because of the fact that we will be probably having another session on wave optics, and during that time, I'm not going to be repeating any of these basic concepts at that time. Okay, so let's just go ahead with this idea that during destructive interference, I is going to be equals to, again, like I1 plus I2 plus 2 root I1 I2 cos of phi. All right, destructive, that means I is minimum. So when I'm saying it's like minimum, then cos phi should be equals to minus 1. So phi should be equals to 2n plus 1 pi, where n should start from 0, 2, 3, and dot, 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 dot. All right, then students, phi is nothing but 2n by 2 pi by lambda into delta x. So we have phi, that is 2n plus 1 into pi, is equals to 2 pi by lambda into delta x. So pi is going to cancel, so which implies your delta x is going to be 2n plus 1 into lambda by 2. So this is what is going to be the phase difference, students, the path difference, okay, for destructive interference, and this is the path difference for constructive interference, okay. So this is what we have. Now, let's take up this next problem that we have out here. All right. So, what do we have in this problem, students? There's a monochromatic light of wavelength 5000 angstrom. Okay. These are all the basics that we actually require, nothing else. Acha. Now, here slit width is D is equals to 1 millimeter, distance between the screen and the slits, that is capital D is equals to 1 meter. If intensity at the two slits are I1 is 4 I naught and I2 is I naught, find the fringe width. Okay, students, now how do we get the formula of fringe width? Number one, fringe width beta is lambda D, lambda small d by capital D. Lambda small d by capital D. Okay. Now, here, acha, let me just derive it for all of you quickly. What is fringe width? It is the distance between two successive. It is the distance between two successive bright fringes. All right, students. So, let's say we just got this formula out here. That is my path difference is d tan theta. That is y divided by capital D should be equals to n lambda for constructive phase difference. That means the position of the nth maxima is going to be n lambda capital D by small d. All right, students. Then fringe width is going to be the position of n plus 1th bright fringe minus the position of the nth bright fringe. So this is going to give me lambda capital D by small d. All right, so this is my formula for fringe width. All right, students, out here, let us have a look. So here, what is going to be my fringe width? Number one, B is lambda. This is a very simple one. All right. So we have got lambda capital D by small d. Okay. So lambda is like 5000 into 10 to the power minus 10 into capital D, that is like 1 meter, divided by small d, that is 10 to the power minus 3. Okay. If you solve it further, you will get 5 into 10 to the power minus 4. I can write it as 0.5 into 10 to the power minus 3 meters. So that is nothing but 0.5 millimeter. All right, students. So this is a very, very simple formula-based question to find out the fringe width. We have something very, very interesting thing coming up as well. Okay. So I just want all of you to sit tight. I'll just give you a glance of that question. So here we have one question. We're going to come to that eventually. All right. So you've got a source out here and we've got a mirror, a plane mirror. The light is getting reflected on it and there's a screen out here. All right. We need to find out the fringe width out here. So students, definitely, we had to know what is the formula of the fringe width in order to finally come here and find this solution. But let me go one step at a time. Slow and steady, we will move ahead. Okay. So students, here first question was to find out the fringe width, and the next question is what? Distance of the fifth minima from the central maximum. So students, in order to find out the positions of minimas, what did we see? We know this is very important. Let me tell you the solution method. You know what? For me, what are the equations that are very, very important? I'll just repeat them once again for all of you. Like, these are always there on my fingertips when I'm like, jumping into wave optics. I always remember I is equals to I1 plus I2 plus twice root I1 I2 cos of phi. That is my first equation. The second equation is delta phi is 2 pi by lambda into delta x. Clear? Students, here whatever you saw just now, some time back, this formula next. If anything else or not, d sine theta for the approximation that my theta value is kind of very, very less, then this is going to become d tan theta, all right? And as a result of which, what I'm going to get is dy by capital T. All right, students, and depending on whether it's like maximum. See, if I remember this, I can actually see this is like the starting point of all the formulas in my physics, okay, of wave optics. Now, see, interestingly, what do we have here? Y small d by capital D. Okay, guys. Now, here, after this, what we can do is, say they are asking for the position of minima. So for minima, sometime back, if you remember, delta x should be equals to how much? Delta x should be equals to this. 2n plus 1 lambda by 2. Wow, so nice. So 2n plus 1 into lambda by 2 should be equals to dy by capital D, which implies what is the position of my nth minima? It is equals to 2n plus 1 into lambda capital D divided by 2d. All right. So that's the formula we have for the position of the nth minima. Achha, listen, students, this n starts from 0. So if I am talking about the fifth minima, so students, that's what I was summarizing. These are the three important formulas I usually remember all the time when I'm dealing with wave optics. Rest everything falls into place. Okay. Now here the fifth minima, if I'm talking about, then the value of my n should be equals to 4. All right. Then the position of the, definitely I can't write it as like, nn plus 1th minima I will be talking about. So here I'm going to get, so they have asked this what? They have asked the distance of the fifth minima from the central maxima on the screen. So the central maxima is just like, the axis, the origin, all right? So for the fifth, it is 2 into 4 plus 1, 2 into 4 plus 1, into lambda is going to be like 5,000 angstrom, 10 to the power minus 10, into the distance between them, capital D, is 1 meter, all right? So this is like 1 meter, and students, this is going to get divided by 2d. So 2 into d, d is how much? 1 millimeter. Okay, so that's like 10 to the power minus 3. That's it. Okay, what do we do? Solve it ahead. What do we get? 9 divided by 2 into 5 into, we have this as 3 zeros and 10 to the power minus 4. All right. So here what I'll do is, I think we can just go ahead and solve this thing out here. I'll take a 10 out here. All right. So this will become like 10 to the power minus 3. This will be like 2. So this is going to be 9 by 4 millimeter. So 9 by 4 millimeter is approximately 2.25 millimeter. So I think students, very, very formula based question that we can actually look here. Now, importantly, this is one important question out here. How do we look at these kind of problems? That is, what is going to be the intensity at y is equals to 1 divided by 3 millimeter? Okay, so let's just have a look at this. How do we deal with these questions? Let me just tell you. They want us to find out, okay, if you can excuse me for a second, students, just give me 2 minutes. All right. I hope this is clear to everyone. Okay. So we need to find out what is going to be the intensity at the rate y is equals to 1 divided by 3 meters. Okay. So this is what the 1 divided by 3 millimeters. My correction. 1 divided by 3 millimeters. Now students, how do we do these kind of questions? Okay. Now they have, obviously it's not going to be maximum also, it's not going to be minimum also. Maximum is like, corresponding to 4 I naught. That's what it is. Okay. And minimum is like 0. If both the intensities were supposed to be the same coming from the two different sources. All right. Now here what do we see, students? We need to find out I at y is equals to 1 by 3 millimeter. Okay. So students, the technique to actually proceed ahead with these kind of questions, all right, is to find out what is going to be the corresponding path difference corresponding to y is equals to 1 by 3. From there, you find out the corresponding phase difference and then use it in this equation. All right, because I1 and I2 is given to you. If you look at it, I1 is this, I2 is this. So in that equation, what did you require? You required actually you actually require this. All right, students. So once you get your phi, you should be able to easily calculate what is going to be your I. All right. So let's just go ahead. So we need to know from y the relation between y and delta x. Okay. So how do we go ahead to find out the relation between y and delta x? So here in this, what will we do? We know it. We have it from this particular formula. All right. This one. Delta x is equals to dy by t. So we know my delta x is equals to y, okay, into tan theta. So that's going to be like d divided by capital D. Okay. So putting down all these values out here, we'll be able to get my delta x. Okay. So that is like 1 by 3 into 10 to the power minus 3 into small d. Small d I think is equals to 1 millimeter out here. So that is going to give me 10 to the power minus 3 again. And then this is equals to how much? This is equals to just 1. And delta phi corresponding to it is going to be equal to, okay, 2 pi by lambda into delta x. So that is going to be like 2 pi divided by 5000 into 10 to the power minus 10 into 1 by 3, okay, 1 by 3, that is my delta x, into 10 to the power minus 6. Clear, students? Acha, if you kind of solve this, you will get the answer as 4 pi by 3 radians. So delta phi comes out to be 4 pi by 3 radians, my dear students. And then, excuse me for that. And then if you happen to kind of want to know what is the intensity at 1 by 3 millimeter, let me take a fresh page rather. All right, it is going to be equal to I said to you is I1 plus I2 plus 2 times root of I1 I2 cos of phi. 4 I naught plus I naught plus 2 into 4 I naught square, all right, into cos of phi, that is like 4 pi by 3. Students, if you solve it, this becomes 5 I naught plus 2 I naught, clear? We get a minus, you get a 2 here, and you get a minus 1 by 2 here. So overall, this comes to 3 I naught. All right, students. So this is what is going to be the intensity, students, where at a point that is 1 by 3 millimeter from the central maxima. Okay, students, let's get to the next problem out here. Now, this is kind of interesting. This is like very, very interesting. All right. Now, before this, let me explain to you a certain concept which is kind of really, really important. That is, let me take up this slide here. All right. Now, students, here in this particular case, what we are going to do is we are going to find out, like, what is the maximum order of maximas and minimas that we can actually be having. Okay. And when can I, like, not use, or what is the limitation of delta x being considered as equals to dy by capital D? I mean, I can't use this always. I mean, like, only under the circumstances that my theta is like very, very small, I can use it. Okay. But if my theta is like large, appreciable enough, I cannot use this. So what is this limitation, or like, what is the difference, or where are the limitations of using this particular formula? Let us just have a look at that. Okay. Acha. Now, students, you must have observed that delta x can be written as like n lambda. Then this is for maxima, like, what is the maximum order of maximas. This can be written as dy by capital D. Action. Now, can I write down my y by capital D is equal to n lambda by small d. Okay. Now, students, we know that these values of thetas are less. Okay. Now, as long as they are less, it's pretty much fine. Now, these things definitely has to be much, much less than 1. Okay. As such, y is like very less and d is much higher. Okay. So, n should be what? Less than d divided by lambda. Achha. Students, as long as n is less than d divided by lambda, okay, or let's say if it is much, much less than d divided by lambda, this equation is valid for much, much less than 1. But if it is like comparable, the value of n and d by lambda is comparable, then students, delta x should be considered as simply d sine theta. Let me give you an example. The best way to explain anything is to give you an example. So the limitation will hold out here. Chalo, we have taken this question out here. Let us look at not required. Let us look at what should be like n equals to. From here, we have just seen n. Let's calculate the value of d by lambda. What is d? 1 millimeter. All right. And lambda is 1 by 2 millimeter. So n is equals to 2. Okay. Find the distance of the first and find the distance between the first and central maxima. That means the distance of the first maxima from this point. So when I am talking about this, here the value of d by lambda is just 2, and I am talking to you to find out the distance for the first maxima. Compare these two values. Is one much, much less than 2? Definitely not. Okay. Then what is going to be the value of your delta x? Now, in that case, my delta x is considered as, my dear students, y sine theta. All right. Now, here, what I'm going to do, okay, just have a look at it using this particular. So, coming to this question, once again, we saw just now what is the limitation of actually using your delta x is equals to dy by capital D, my dear students. Okay, we know for sure that my delta x is generally used as this, but we just saw in a slide back that n has got a maximum value, like that is equals to d by lambda. All right. So n should actually be like if I'm asking you the position of the nth maxima, then that nth value should be much less than d divided by lambda. Okay. So here they have asked me for the first one. So actually, like your one should be much less than d divided by lambda. If I check it in this case, is 1 much less than 1 divided by 1 by 2? That is nothing but equals to 2. Is this true? No, not at all. 1 is not much less than 2, my dear students. As a result of which, we cannot use this as the path difference, okay, formula. Then what should we use as the formula for your path difference? The formula for the path difference then in that case is going to be the general one, that is d sine theta, and in this case it should be 1 times lambda, that is n lambda, okay, which going to give me that my sine theta is going to be like lambda divided by d, so that is like half, which implies theta will be equals to 30 degrees. All right, theta being equals to 30 degrees, what do I get, my dear students? Simply y divided by d is nothing but tan 30. So the position of the first root 3 and d I know is equals to 1 meter. So y should be equals to 1 divided by root 3 meters. Okay. So that is going to be the distance of the first maxima from the center of the screen, my dear students. Okay. So I hope that is pretty much clear to everyone. Okay. Now let's go ahead. Let's look at a very similar question. Okay. Of the same sort which is being produced out here. Rather, I would say, why don't all of you take this as your homework, and so that we can proceed to the last question, okay, which I had told you, and we'll just go to that question directly. So this could be like one of your homework. You can take a snapshot of this with you guys. And going to the last question out here, we want to find out what is going to be the fringe width in this case. Now, students, see this. This is a very interesting problem. Okay, and how is its ray diagram going to look like? It is going to look like something like this. A ray is going to come, hit this plane mirror. So this is a plane mirror. So if you see this, it's a ray coming and hitting at the plane mirror. It is hitting at an angle theta. It is going to go and strike here. All right. Now, students, one ray is going to go directly from this source. Call it as S1, call this as S2. So one ray is going to go directly and hit this source out here. All right. Another one is like, a reflection of the source. So now these two, the original and the reflection in the plane mirror, acts as the two sources, which is going to create interference. All right. So that is the entire logic out here. So my dear students, this and this going together is going to give me the interference out here. They want us to find out what is going to be the fringe width. FRINGWIDTH. Students, I hope everybody remember what is the formula for fringe width. Beta is equals to lambda capital D by small d. Lambda is given to us 440 nanometer. So lambda is 440. So what they want us to find out fringe width, beta is equals to lambda capital D by small d. So students, what is going to be capital D in this case? Very simple. It's going to be the distance from here to the screen. Now, what is going to be this distance? It is very simple. All right, if you look at it, this, my dear students, S to O, it is 20 centimeter. So what is going to be this distance from here to here? This distance is simply going to be equals to 20 cos theta. So 20, this distance is 20 cos theta. Now students, if you observe, theta is a very small angle. Now for a very small angle, cos of theta is going to be simply equals to 1. So this is going to be just equals to 20. So this distance capital D is going to be 120, which is like this 100 plus this 20, 100 plus 20, that is 120 centimeter or 1.2 meters. Clear? Now what else do we need, my dear students? We need this small d. Okay. Now the image is going to be formed out here. All right. So image of this particular source. So what is this? This is my small d, students. Okay. Interesting enough. So this small d, how do we calculate it? If this and this, they are kind of symmetric, they're equal. So this is given to us as theta, my dear students. So 20 sine theta is this value. 20 into sine theta. So students, can it, and I write it as 20 into theta, because for very small angle of theta, sine theta is approximately equal to theta. Clear? So theta's value is given to us is 0.5 into 10 to the power minus 3. So I can write this as 20 into 0.5 into 10 to the power minus 3. So that is nothing but equals to 10 into 10 to the power minus 3. So that is like 10 to the power minus 2. All right. 10 to the power minus 2. What? In terms of, it's like centimeter into theta. So that's going to be in centimeters. Clear, students? So you get the value of your d. So the total distance is going to be 2 into 10 to the power minus 2 centimeter. All right, bring it to meters, convert it into meters. So 2 into 10 to the power minus 4 meters. We know the value of small d. We know the value of capital D. So beta will be equals to lambda, that is 440 into 10 to the power minus 9 into capital D is like 1.2 divided by small d. Small d's value is 2 into 10 to the power minus 4. 2 into 10 to the power minus 4. Students, this is what is going to be the value of your fringe width. Okay, so you multiply this becomes like 220. All right, so this will be like 220 into 1.2 into 10 to the power minus 5. Okay, or rather let's say 22 into 1.2 into 10 to the power minus 4 is what is going to be the answer out here in terms of meter. This is going to be the fringe width. Okay, so I think you can even solve it further if you kind of, excuse me. All right, so if you kind of solve it even further, you will get the answer as 44 and then 22, so 264. 2.264, so that's like 26.4 into 10 to the power minus 4 meters is what is going to be your answer. Okay, so students, that's all we are going to give for our today's session in the course that we are coming up with. We are going to be completing the entire crash course of your JEE mains in 30 days. All right, which is going to start from students on 22nd of November. All right. Now, in this, you need to just click on this link and go to this link and register yourself for the course out there. Now, we will try to cover up as many questions as possible during these particular sessions. Rather, for this session out here during our masterclass, what we tend to do is give you the very basics, whatever is required for the questions in the the topic and all. Okay, the basic concepts and the basic theory that is required. Wherein in our sessions, what we'll try to do is more JEE based questions of both mains and advanced, that has come in our previous years. All right, like we took up the last question, okay, just now, which you saw. Okay, like this question. They're like pretty like tricky, and like they are not like your regular questions. All right. So we're definitely going to take up these kind of questions during the sessions, and within, let me tell you, my dear students, all the teachers out here are so passionate, and like they're always like seeking ways of finding out new methods. They're inventing new techniques of teaching the students in better and better manner. So it's like optimizing the time to 30 days is going to be like awesome, okay, where you can have a wonderful experience with the teachers out here. Every day between 5 to 11 p.m. in the evening, you will be having 2 to 3 sessions for the next 1 month, in which your entire JE syllabus is going to be covered. All right, students. So thank you very much, all of you. God bless you. I hope everybody liked the session today. If you liked it, definitely go ahead, click on the link and register yourself. But before that, go ahead, like the video, all right, and also subscribe for our channel, okay? And God bless you all, and see you soon in my sessions on JEE Mains, okay, in the crash course. God bless you, and thank you, all of you students. Bye bye.